Hi, thanks for coming. Welcome to my talk on Asterisk and the social Internet of Things. My name is Mike Walton. I'm co-founder and CTO of Far South Networks. That's a manufacturer of Asterisk-based PBXs. I'm also heading up development at our new web-centric venture, WonderWeb. Just a little about me first. I started out 22 years ago as a hardware development engineer at Alcatel, with embedded software development following soon thereafter. I became interested in open source and Asterisk about 10 years ago. At that time, I co-founded Far South Networks, where I headed up the development of an Ethernet-connected PSTN adapter for Asterisk, which we continue to sell to this day. I moved on to developing integrated Asterisk-based PBXs based on an in-house embedded x86 platform that we designed. Lately, my pet project has been the Asterisk-enabled social network for small business users, WonderWeb. That is built with a bunch of open source technologies, including Java and Tomcat, Node.js, AngularJS, and of course, Asterisk itself. Far South Networks is based in the city of Cape Town, South Africa, which is famous for Table Mountain and its amazing coastal scenery, which I thought I'd show you a little bit of. Recently, we've started WonderWeb in Auckland, New Zealand, another coastal town, where I've been based for the past 2 years. So what about Asterisk and the social Internet of Things? I'm going to talk about how we put together some technology jigsaw pieces and ended up with something a little bit new and unique. I'll show you how Asterisk has a place both in the social internet and in the emerging Internet of Things. We'll have a look at the benefits of promoting Asterisk systems to first-class netizenship by equipping them with the same 3 Ws that human-driven devices use to communicate on the web, and that's WebSockets, WebRTC, and web apps. I'll share some notes from our journey with Asterisk on low-cost yet powerful ARM-based devices that have arisen from the mobile revolution. And finally, I'll demonstrate how this all comes together with a couple of live social calls. So here's my agenda for the next 30 minutes or so. First of all, we'll just look at social networking and the Internet of Things in general, how this new paradigm is emerging, incorporating these areas into a new conceptual layer of the web. Secondly, I'll highlight some of the key technologies enabling the next phase of global networking. Thirdly, I'll share some details of our Asterisk thing, this little blue box that you may be able to see on the table over here, and how it leverages some of this new tech to full advantages. Finally, I'll demonstrate a real-world application that brings together all these different pieces to reach our business goal, which is low-cost but highly featured unified communications and mobility for small businesses. So let's get right into the Internet of Things and its social aspects. We all know and love Asterisk. That's why we're here. And I'm sure many people here have had long relationships with Asterisk PBXs in various forms. These PBXs are network-connected things that we interact with using specialized knowledge. And we've seen that they behave mostly predictably and with repeatability and lend themselves to automation and network distribution. The Internet of Things is all about automation and distribution on a grand scale, through carefully regulated machine-to-machine interactions. So what happens if we apply some Internet of Things thinking to our Asterisk world? At the same time, the social internet has embraced real-time connectivity for instant message, video, and voice. So where does Asterisk fit into this picture? Okay, well, let's start with what is this Internet of Things? Well, here's a very comprehensive but long-winded definition from CERP in Europe that I'm going to read to you. Internet of Things, or IoT, is an integrated part of future internet and could be defined as a dynamic global network infrastructure with self-configuring capabilities based on standard and interoperable communications protocols, where physical and virtual things have identities, physical attributes, and virtual personalities, and use intelligent interfaces and are seamlessly integrated into the information network. In the IoT, things are expected to become active participants in business information and social processes, where they are enabled to interact and communicate amongst themselves and with the environment by exchanging data and information sensed about the environment, while reacting autonomously to the real or physical world events and influencing it by running processes that trigger actions and create services with or without the direct human intervention. Interfaces in the form of services facilitate interactions with these smart things over the internet, query and change their state and any information associated with them, taking into account security and privacy issues. Well, that is word soup. The IEEE has a document toward the definition of the Internet of Things, towards, not there yet, and it's 86 pages long. So personally, I prefer this more succinct definition from Stephen Haller at SAP Research. I'll let you read it. So by its very nature, the IoT is difficult to define and encompasses a broad range of disparate hard and soft technologies, from sensors to embedded computing devices to network and telecoms to web and cloud applications. And as a result, we have multiple difficult problems to address. Perhaps first and foremost, security and privacy. With the internet as its underlying network infrastructure, IoT potentially exposes any participating device to global security risks. Criminals and hackers have the same access to the internet as do you and I. You've got to love the title to a presentation given at DEF CON hacking conference last year. The hand that rocks the cradle, hacking IoT baby monitors. And then there are governments to worry about, and even worse, marketing departments. So other than the obvious security challenges, there are other multiple hazards to look out for on the road to IoT success. So let's look at standardization and interoperability. Well, we have no clear boundaries of definition, as we've seen, for IoT, so it's impossible to arrive at a fixed set of applicable standards at this stage. In fact, the standards base is as diverse and variable as the set of technologies in play. This results in major interop challenges. Standardization bodies such as IETF, IEEE, and ETSI all have working groups for IoT, and there's a host of alliances. To add to the chaos, there are powerful competing industry players in the mix. Then there's complexity. The IoT is less well-defined, yet far more complex than the internet or World Wide Web alone. And finally, there's a lot of hype at the moment around IoT, so it is often hard to see the wood for the trees, or cactuses in this case. So what do I mean by the social Internet of Things? Well, overlaying the well-defined social network paradigm, as we know from Facebook, etc., brings some structure and order into the system. For example, a social network introduces human and organizational elements and their roles in the highly connected world. Social network defines relationships amongst these elements, giving us a model for visibility and connectivity amongst humans and groupings and the smart devices themselves. So with this, we gain a model for who sees whom, who sees what belongs to whom, etc. This helps us enormously in defining privacy and security policies and limiting the scope of interactions. We also gain the inherent communications power and flexibility of the social network model with its concepts of subscription to services, distribution, shared content, and resources, and of course, its global reach. But because we're PBX folk, I'd like to illustrate a vision of the social IoT with a more relevant example. Let's imagine a corporate PBX environment. It could be on-site or hosted. I'm going to describe some relationships and interactions based on the human, organizational, and device elements you see in the picture here. So, Kate and Jim are colleagues. Kate and Jim work for Acme. Acme owns a PBX and extension 555. Jim owns his mobile. Jim's mobile has a UC app for communicating with a PBX. Kate has exclusive use of extension 555. Now Kate calls Jim on his mobile, etc. So we see that something that looks like a social graph emerging with different relationships amongst elements. The visibility, permissions, and information flow can be modeled in a social networking paradigm. For example, Kate's social network relationship with Jim allows her to see whether he is available. Jim's availability is determined by the UC app running on his mobile. So let's look at the specifics of bringing Asterisk into this IoT model. We'll put aside for a moment the social networking aspect. 4 important capabilities around Internet of Things devices or things are, number 1, unique addressability. Everything needs to be able to be named and identified in a globally unique manner. Number 2 is virtualization. The thing is modeled in software. The physical thing must be easily replaceable, since its function and role, which are the things that make it useful, are longer lived than the thing itself. To put it another way, in a service-oriented world, we buy and sell capability and function. We are less interested in the vehicle providing the service. Thirdly, capability for real-time interactions over the internet. This is the reason for being of the IoT, after all. It facilitates interactions amongst people and things in real time in order to achieve service goals. And fourthly, The IoT model gives us specialized, less broadly capable things being brought into the IoT using proxies. So let's see how Asterisk could stack up in each of these areas, or what we need to do to make it fit. So unique addressability. Well, DNS would be the natural and obvious choice for an Asterisk box. But with the IoT, we want to support NAT and strict firewalling with no inbound access, both for security and for ease of deployment. So instead, we provide a cloud-based registration service for the PBX thing. Our system, WonderWeb, for example, uses a serial number combined with an X509 certificate stored on the device. On initial registration, WonderWeb allocates a unique URI to the PBX, and that becomes its address for identification. Then there's virtualization. We model the features and state of our addressable resource, the Asterisk PBX, in the cloud. This soft model allows us to interact with the PBX as an always available service, independent of the physical hardware state. For example, the PBX could be provisioned prior to being physically installed. The URI address that we allocated above is the path to the virtual model. Thirdly, what about real-time internet interaction? Well, we're all familiar with SIP for signaling and RTP for media. Those are part of the real-time interaction. We also add a control and management flow, providing the link between the virtualized model and the physical PBX. We also need to provide a means of actually getting all the flows through the internet securely. And then what about gateway and proxy? Well, actually, an Asterisk PBX is ideally placed to be an IoT gateway or proxy to the ecosystem around it. The local network and the IP phones on that network are not natively compliant with IoT, but if we introduce a proxy layer into the PBX, we can represent these assets into the cloud model. We've established how Asterisk might fit into the Internet of Things. Let's look at the social networking layer. There has been an enormous market-shifting trend in social networking in the past few years, and that's instant messaging. That has naturally led to voice and video-enabled applications that include a social networking element. In a public Q&A session in November 2014, Mark Zuckerberg explained, messaging is one of the few things that people do more than social networking. And of course, the context is Facebook's acquisition of WhatsApp the previous month. WhatsApp introduced voice calling in 2015. Facebook Messenger had already prior to that. And it's well known in the WebRTC world that both Messenger and WhatsApp draw heavily from WebRTC standards and open source projects. That should get us excited, since Asterisk was one of the early adopters of the technologies underlying WebRTC. Asterisk WebRTC capability is a crucial piece of the puzzle for integrating with web and social networks, since it deals with the concerns of real-time interaction, security, network traversal, and interoperability. So to bring a telephone system like Asterisk into the social arena, we need to recognize where a person's telephonic presence fits into their overall net identity. When we call into a company, we normally want to reach a particular person or a particular department. In either case, having to look up the number and dial it is, well, a quaint legacy, really, in today's environment. E164 numbers are expensive, they're arbitrary, geographical, difficult to remember, and worst of all, they're administered in old-fashioned and non-democratic ways in many countries. We have much better ways, post-globalization, of identifying people and departments: email addresses, web page URLs, social media account IDs. Having said that, the PSTN isn't going away for a while yet, and traditional voice over IP is now mature and actually looking rather a lot like an extension of the PSTN itself. Just as Asterisk has proved to be a great connector of legacy PSTN with voice over IP, with the addition of WebRTC, it adds to these talents a propensity for over-the-top services and web-centric voice and video. What we want is to aim for the single federated identity and presence that is probably best embodied in the smartphone. Because where my smartphone is, that's where I am. And it's not about my mobile number anymore, but about my online identity. Sorry, let me go back one. WebRTC allows us to exploit Asterisk's legendary voice communication abilities in a web-based social networking context. We can now call from inside a web application. For example, click here to speak to an agent from inside a product page. So a picture starts to emerge of Asterisk interacting with the new web through its WebRTC capability for real-time voice and video, and by introducing an Internet of Things nature for real-time managed service. I'll take you briefly through some of the enabling technologies that we can apply when bringing Asterisk into the social IoT. Asterisk has always had comprehensive language-agnostic APIs such as AMI, AGI, etc. More recently, we see HTTP with WebSockets, and we see the ARI REST interface. So let's just look at how do WebRTC and Asterisk fit together then. The good news is the standards for WebRTC have matured and settled considerably over the last year or so, and we heard this morning that one of the key codecs in WebRTC, Opus, has now been included in the Asterisk stream. The implementations have seen good battle hardening over the years, and it's important to note that the Asterisk implementation is not and does not need to be a full WebRTC technology stack, because the endpoint-related functions such as acoustic echo cancellation and noise reduction aren't required. In fact, the elements of Asterisk code related to WebRTC endpoint interoperability are quite minimal. Secure RTP is handled by OS libraries. ICE is provided by PJNath, which is part of Asterisk. Codecs are G711, G722, and, as we've mentioned, Opus. The Opus codecs need not even be built into Asterisk. They're typically available as OS library packages. Just these elements, when combined with a suitable signaling protocol, typically SIP, give us full compatibility with WebRTC endpoints. The very useful WebRTC and Asterisk tutorials that are out there on the web typically use another feature of Asterisk, and that's SIP over WebSocket. It's not always clear from the tutorials that neither WebSocket nor SIP are part of the WebRTC standards. SIP and WebSocket are the most convenient way, though, of integrating web browser-based endpoints with Asterisk. Anyone who's followed one of these how-tos, though, has encountered a basic architectural problem. Asterisk PBXs are usually not HTTPS servers with fixed DNS resolution and authorized site certificates. Web browsers require this for WebRTC applications to work properly. Besides, inbound HTTPS WebSocket support places a global authentication requirement on the server. Who's trying to open HTTPS connections, and how do we know it's an authentic usage? The Internet of Things architecture view of this is that the Asterisk PBX should be a web client, not a server. For security and many other good reasons, the PBX should use outbound connections only. It should be fully shielded behind a firewall. And that will give you Asterisk without the risk. Sorry about the pun. Typically, it'll reside on a LAN behind NAT. Just like any other internet client, it should be deployable anyway. So we have a mismatch that we need to deal with here. Fortunately, WebSockets lend themselves to a back-to-back relay configuration. An agent running on a PBX can open a WebSocket to Asterisk and another one to a cloud service and relay the payload between them. This is possible because WebSockets, once they're established, are pure bi-directional peer-to-peer pipes. Which brings us to what cloud services may be needed to complete this picture. The minimal cloud service needs to provide the following: authentication of web or mobile-based service users and authentication and registration of the PBX. It needs to provide web content for delivery of the WebRTC-based phone services. It needs to provide full bidirectional communications with users and with PBXs for signaling, and that's where we use WebSocket. It needs to provide a signaling relay or proxy function to enable user to PBX interactions. And finally, it needs WebRTC for the peer-to-peer connections, and that carries the media between the 2 points. So we now have anywhere-to-anywhere secure connectivity between Jim and his PBX. No inbound access is required anywhere. Everything is encrypted. In solving the signaling relay problem, we've also introduced a bidirectional channel to the user and to the device, and that can be used for other communication needs, for example, instant messaging or management of the devices. But wait a minute, something's missing here. An Asterisk PBX won't have a browser. Human users connecting to the HTTPS cloud service have either a browser or a mobile app that authenticates and consumes the web content and APIs, using web technologies like HTML5, JavaScript, AJAX, JSON, and REST. Similarly, we need a web-oriented way for the PBX thing to use the cloud services. Enter Node.js. It provides a web-friendly environment for interaction with the service. Although Node is normally associated with server-side applications, it turns out to be a great fit for headless, that is, non-graphical web clients. With Node, we get the Chrome V8 JavaScript engine. We get Node Package Manager. We get an HTTP-centric event-driven architecture. And most important of all, we get access to thousands of lightweight web libraries that are all open source. For our system, we use a simple shell that runs persistently on our device, trying to connect to a known HTTPS URL to download its landing JavaScript. That's all it has to do. From there on, we get delivery of code on demand from the cloud service. The on-demand code uses the same REST APIs as the mobile and desktop apps on a common JS client stack to interact with the service. Just like a conventional web app, it is defined in the cloud rather than on the device, and it's thus guaranteed to be up-to-date and compatible. Feature additions and functionality changes are simple to manage. Some of the functions we currently implement in our node-based IoT client are SIP over secure WebSocket relay. So as explained, we need to be able to open WebSocket to Asterisk, and we need to be able to open a WebSocket to the cloud and relay the data between them to allow for SIP connectivity. Secondly, we do monitoring of event logs on the device and state, and we pass that up to the cloud for system maintenance and monitoring. We also are able to tunnel HTTP, so from anywhere in the cloud, we can access the local HTTP securely on the device. Similarly, we do terminal emulation, so we can access CLIs on the device from the cloud. We have an AMI client so that we can take Asterisk events and relay them up to our cloud instance. And lastly, we have a MySQL client, which allows us to manipulate the on-device database. And of course, being code on demand, that list can keep growing. For example, we could add an IoT agent to control phones on the network. As a quick diversion, I'd like to talk about the use of REST architecture in the web. REST, or representational state transfer, is the language of web APIs world over. To quote Wikipedia, it is the architectural style of the World Wide Web. Embracing the REST approach has given us a uniformity of semantics or meaning across a number of very different systems and software frameworks. REST supports the anywhere, anytime philosophy of the internet extremely well, and because of the basic requirement that resources be uniformly identified by URI. That is the meaning of URI, after all. So no matter what is the current state of my client application, that's its own concern. The URI https lalaland.z's a dog's life will always represent the same underlying resource and its own state as maintained in the cloud. If I want to get a representation of that resource and its state at any time, I simply send an HTTP GET to that URI. The format of the representation is media dependent. JavaScript object notation or JSON is the most popular choice. If I want to modify the resource, I send HTTP put with some new information. Thereafter, any client getting the same resource will retrieve the newly modified state. Similarly, we can use HTTP delete to get rid of it altogether, although we wouldn't want to get rid of him, would we? An HTTP post will allow us to create a new resource. Seen in another way, REST defines a universal and massively scalable API to an underlying object model. And HTTP gives us a built-in support for authentication, caching, content media definition, and of course, the hyperlinks that provide the client with information about state transitions and related resources. Most importantly, the REST architecture enforces strong separation of client and server state, which is critical for web scale deployment. The service does not need to know the presentation state of each client, only the state of its underlying resources. So on that note, let's have a 1-minute break because I know it's been a bit long and wordy. I recommend stand and stretch, but whatever you like to do. This guy over here, if we can get him to play, likes solving Rubik's Cubes underwater. So he'll take us through our minute. That's a 3x3, that's easy enough. I think next up is a 4x4. Anyone ever completed one of those? So let's talk about ARM CPUs. It may seem unrelated, but I'll bring it all together in the end. The CPU industry is changing, and it's changing rapidly. The ARM architecture, from its humble beginnings as the Acorn RISC machine in Cambridge, England, is now by a very large margin the most used CPU architecture. Acorn computers in the early 80s used the 8-bit 6502 processor. The processor also used in the Apple II and many other microcomputers of that era. As an interesting aside, it was a visit at that time, some 33 years ago, to the Western Design Center right here in Phoenix by Acorn engineers that convinced them that they could design their own processor. Western Design was, in fact, the first microprocessor IP licensing vendor with its 6502 and variants thereof. A similar business model was followed by the Acorn team after they returned from Phoenix and designed the first version of the ARM processor core in the mid-1980s. 30 years down the line, the numbers speak for themselves. 14.9 billion, that's a lot of processors in 1 year. Look at that in comparison to Intel. ARM corporate information indicates that more than 86 billion ARM processors have been shipped to date. Quantity aside, the relentless advancement of the processing power and efficiency of these devices has been phenomenal, driven largely by the mobile device market. They've proven unbeatable for all practical purposes as far as cost and power efficiency are concerned. And let's be honest, most applications are increasingly cost and power sensitive in our resource-constrained and competitive world. Not long ago, the lack of any kind of overall architecture definition for ARM-based systems made every project based on these systems a full-scale embedded development, with custom builds for everything from OS through libraries and even toolset. However, there's been a nice convergence of the ecosystem lately, and nowadays many ARM-based single-board computers are well supported by mainstream Linux distros. So what about Asterisk on ARM? Well, Asterisk has, of course, historically been deployed mainly on the x86 architecture. So why would we want to build an Asterisk-based system on an ARM platform? Number one reason is lower system cost for equivalent performance and features. Volume pricing for a typical high-performance ARM system on chip is about $10 to $12. Complete single-board computers start at about $35, e.g. Raspberry Pi 3. This pricing is largely driven by the mobile market, tablets in particular. And then there's power consumption. These single-board computers use not much more than a few watts under typical conditions. That means they run cool, there are no fans, there's nothing to gather dust or seize up. All of this improves reliability. Some of the concerns we had before taking the plunge and developing an Asterisk PBX on ARM were, first of all, performance. Secondly, portability of software and compatibility with our existing code base. And thirdly, what about the build environment? I'll relate some of the experiences we had. So what about real performance? We used a quad-core Cortex-A9 as our base. What we do to evaluate performance typically is we run multiple high-complexity voice codecs, such as Opus or G729. We found that this is commonly the bottleneck for performance in smaller systems. We were aiming for a system that could handle 8 simultaneous transcoded calls, which is typical for small business apps. What immediately astounded us about this low-cost, low-power platform was its talented number crunching. We found we could easily do 16 simultaneous Opus encode-decode sessions for 8 kHz audio with just 36% usage of the 4 cores. This suggests up to 24 simultaneous compressed calls with good CPU margin remaining. That's easily a 50 to 100 user PBX. Testing the full bandwidth Opus codec at 48 kHz yields similarly encouraging results. Other tests that we did showed that network and I/O performance on this platform are more than adequate for small business type systems. So what about portability? We wanted to achieve close to 100% full lifecycle code sharing across x86 and ARM. At the heart of this approach is selecting a Linux distribution that's well supported across both platform types. For us, that was Ubuntu, particularly since it was our historical distro of choice. Of course, there are other equally valid choices here too. Ubuntu gives us public repositories with thousands of common open source packages pre-built for ARM. Once the initial boot and kernel port are done, the software ecosystem just works as per x86. We already use a customized kernel for our x86 products, so the fact that we had to build a customized kernel for ARM was not a problem. Packages that we custom built, like Asterisk itself, pretty much just needed minor packaging tweaks to build successfully for ARM. So what about the build environment? Establishing a solid automated cross-build environment is essential, and this is often a point of uncertainty for developers used to the classic build for x86 on x86 approach. We've used the Debian build and packaging tools for our x86-based systems because it makes it easy for us to achieve repeatable builds and make use of the excellent HTTP repository tools. The Debian and Ubuntu packaging teams put a lot of work into developing a standardized multi-architecture and cross-build capable toolset, which they call S-build. It creates a chroot environment with the correct distro version, foreign architecture, and cross-compile tools and libraries needed to build completed packages for the foreign architecture. It takes care of cross-build complexities such as architecture-specific headers and development libraries. It also handles running in-source build time tools, which is a common bugbear for cross-builds. It does this by emulating the foreign architecture using QEMU. With S-build, we get a single toolset that allows us to build for x86 or ARM from the same source code on a common platform. So some of the challenges you may face if you decide to move to ARM are OS support. Well, it's mostly good news. There are many generic ARM architecture Linux distros available these days. Typically, the only work you need to do is on configuring or perhaps patching the kernel. We obtained a stock Android kernel from the vendor, and we just made minor mods, mostly to config flags, to make it work smoothly with Ubuntu. Once you've got the kernel up and running, the precompiled packages from upstream should just work. Then there is boot and onboard flash. Booting is typically a bit different on these systems. Normally, it's a proprietary fixed bootloader which reads an image from flash and executes it in memory. We developed a set of scripts to integrate the update of kernel and initRD images with the normal Debian-based tools. So for us, upgrading in the field is simply a case of apt-get install my shiny new kernel. The file system, well, that's pretty simple, provided the kernel includes a proper way leveling flash driver. So we use ext4 with full journaling, and it's proved solid and reliable. External SD cards have built-in way leveling, and they just work. Local console, our platform doesn't have a local console connection, so we use USB on the go with virtual serial and network devices, which allow us to tether it to a PC. And lastly, the build environment. So I'll say it again. For production, it's essential to have a solid, repeatable, cross-compiling build environment. Once you've got that in place, the target architecture fades into insignificance. And what do you get out of it? Well, that makes all the effort worthwhile. We get a small, low-cost, low-power Asterisk appliance, as what you see over here. And that has the full power of a Linux server and a virtually unlimited ecosystem of tried and tested software available. Well, that was a lot of moving parts that we've covered. So I'd like to show you how it all comes together to solve our business need. I'll be demonstrating our cloud-based service, wonderweb.net. There we go. That integrates simple social networking with instant messaging and presence. It has an Internet of Things aspect for device integration, and it supports WebRTC for anywhere, anytime voice. The little blue ARM-based PBX, Wonderbox, will be providing the PBX service through its plain outbound internet connection. And you can see it's just got power and Wi-Fi, that's it. My Android phone will be connected to the internet using its own 3G connection and a custom app that's installed on it. My PC will have a separate session to WonderWeb on a normal Chrome browser, which I'll bring up on the screen. Incidentally, the mobile phone has many IoT characteristics itself when you think about it. It is a managed, uniquely identified, always connected device. We use the cloud push services provided by Google and Apple to activate the app on the phone and alert the user for incoming calls and messages. So by wiring a push service client in the cloud into our SIP proxy in the cloud, we can fully integrate call alerting to sleeping mobile phones. So let's try and switch over to some live views and see how it all comes together. Right. So I think for this, I'm going to show you what I've got on my screen. Let's go back to the home page. That's not coming through. Okay. Not sure why. I think I need to go over here. Now it's come through. Right. So this is just a standard Chrome browser view into our cloud-based app. And it's got the usual kind of chat, group chat, those sorts of things. But what I'm more interested in showing you here is if you look to where I'm pointing over here, that represents that little blue box over there and its current state. So what I can do is, let's see. Right, what I'd like to do is just give you some idea of how that box actually connects to the cloud, downloads its IoT client, and begins the process of becoming part of this distributed voice app. So what I can do here is I can go into an admin mode. I can search for that device. And I can quickly show you how, first of all, there's a virtual model of this device. So it's got extensions, for example, that we can configure here in the cloud, and those can be synchronized onto the device. And those extensions associate users of this system with extensions on that device. I can open a command line interface. And let's go into the Asterisk CLI. So what's happening there is, without any inbound access to that box, we're actually getting a tunnel through from my normal web view into that box's CLI. Now, there we go. So, just two things I want to do. I want to make a call to this user over here. And let's have a look at the CLI while we're doing that, if we can, so that you can believe me that it's actually happening on that box. So on my mobile phone, I'm going to hopefully call into the user that's logged in currently on my PC. Just give me a second. Okay, there we go. Everything's slow in a live presentation. Right, let's see if this works. Right, so I made a call from my mobile app, which you may be able to see a little bit of. And it might take a little while to complete through all the networks, but there we go. And that's ringing over here. I think it's not liking the full screen, but let's just try and answer it in any case. There we go. So, if that's working, you'll be hearing me over the PA. All right, so that's proof of that call. Just one more. If someone would volunteer to dial a 1855 number, then you can also have something to say. So if you just give me a second over here. There we go. Right, who's going to volunteer to dial a 855 number for me? There we go, second row there. Make sure you got something important to say. I think I'm on the right extension here now. All right, so the number is 855-535-8260. Incidentally, that's working through an instance of our PBX that lives in the cloud. So here comes a call from, hopefully that's your number. Say something important. There we go. Right, so that's just showing some PSTN integration, going into a PBX that's running in actually a Google Computer Engine instance, and the extension running on my laptop through a normal internet connection is receiving the call. So I think that shows how some of these things come together briefly. So are there any questions in the remaining time?
We have time for one, maybe two very quick questions, if anybody has one. It's a pretty impressive demo on a very little ARM-based box there. It's fantastic with Wi-Fi, and that's running off of Wi-Fi?
Yeah, so that's actually connected to a mobile hotspot on my phone to get its connection to the internet.
All right, so I mean that's a dangerous demo right there. That's fantastic.
Maybe I should do it tonight.
I think you should. Yeah. I'm recommending it. Any questions that you might have? Yes.
What kind of optimization did you have to do to have Asterisk?
The question is, what kind of optimization did you have to do to have Asterisk on that?
Right, so those performance figures involved no special optimization. That was straight library code. And overall, we didn't have to do any. That box is quad-core. It's got 2 gigs of RAM. That's more than enough for Asterisk to run plenty of calls.
Do you have any stress testing on how many simultaneous calls you've had on a box like that?
Yeah, we've tested them up to about 16 simultaneous calls, but that's very unstressed at that level. We also run Java on that box, Node, MySQL. It's got free PBX, so it's a fairly big installation on those boxes, and honestly, they cruise.
Yes, sir. The cost of the actual device.
So the system on chip that's the heart of that box is about $10 to $12. It's a Rockchip quad-core 1.6 gig ARM device. But we buy in the finished single board computer, and it's a bit more than that. I think it's $50 or $60. But it's very similar spec to something like a Raspberry Pi 3, which is $35, I think.
All right. Thank you all very much. How about a big round of applause?
Thank you. Thanks very much.